So there are some small nuances in writing equilibrium constants that need to be discussed. And this one is kind of a major one. Let's think back to the example that we did about the dissolving and crystallizing example. Or we could think of like the butane vaporizing as compared to condensing. And so in this case, we're talking about the solid calcium hydroxide dissolving in solution. And so what we can do is we can think of this as a chemical reaction where we take solid calcium hydroxide, and when we put it in solution, it becomes the calcium positive 2 ion plus 2 hydroxide ions, because calcium hydroxide is CaOH2. And so we could think of that as a chemical reaction. The question is, how could we write that as an equilibrium constant? Well, here's how. I have some work pulled up by one of your peers because he did a really good job on this graph. And if you remember doing this in this lab, this was when we were doing that awesome game. And no matter what we did, whether all the particles started on the solution or all of them started in the solid calcium hydroxide, it always ended up 20 and 10 at equilibrium. And so you generated graphs that look like this, but then you also got the graph that looked like this. So let me ask you this. Remember that we write the rate equation as being equal to, let me just scroll down here for a second. Let's say we write the rate of the forward reaction should be equal to the constant of the forward reaction times the concentration of whatever the reactants are. And then if you remember, the rate of the reverse reaction is equal to the constant of the reverse reaction times the concentration of whatever your products are. So in this case here, we're talking about calcium hydroxide dissolving. So therefore, we could write the equation as CaOH2 as a solid. And then I could do the equilibrium arrow, but I can't really do that very well other than like this. And then I could say that's like the calcium ion in the aqueous state, AQ, plus 2 hydroxide ions in the aqueous state. Like that. And so then my reactants here would be the calcium hydroxide. And then my product would be the calcium, but then I'd also have to multiply that based on this, based on what we talked about in the previous video, OH with a negative. I should have had a positive 2 on the calcium. I'm not going to go back to fix it. But then I have to square it because there's a coefficient of 2 in front of that. And so that would be my rate before I get into the equilibrium constant. Therefore, I have a problem here. And I'm going to show you this by showing this. The forward rate is dictated based on the calcium hydroxide, okay? So I want you to look at this graph that Andre made here. The forward reaction is being dissolved. The reverse reaction is the solid. So let's just look at this. If you remember, the first one was when we started all in the solid phase. And what you'll notice is the dissolving part gradually increases over time. That's because there becomes more particles in solution. Therefore, the rate of dissolving is based on the rate, how many calcium and how many hydroxide ions you have in solution. So therefore, it seems to make sense, based on this, that this one holds true. Let's look at the other one, the yellow. Gradually, this is when 30 particles were in the dissolve phase. Gradually over time, it lowered. That's because it was dictated by the number of calcium and hydroxide ions present in solution. If you have a lot, then there's going to be a higher rate of dissolving. So now let's think about the other process, being dissolved, going from a solid to dissolve. So the yellows represent the crystallization process. I was looking at him and it was kind of weird. So it's crystallization. So the rate of crystallization is dictated based on the concentration of whatever's in solution. The rate of dissolving, however, it stays constant the entire time. In other words, it doesn't matter whether I have a lot, 30, or like none over here, it's always going to be the same. That is huge because when I write this equation here, the rate of the forward reaction is not dictated based on the concentration of the calcium hydroxide solid particles. It doesn't matter. It's always going to be the same. So therefore, we don't include it in equilibrium constant expressions. Therefore, we would write this equilibrium constant as follows. K EQ is equal to the concentration of my products, calcium ion times my hydroxide ion, square it like so, and then that's it. I wouldn't divide it by anything because the reactance is nothing. And so therefore, that's how we would write equations. In general, you never write solids in equilibrium expressions. The reason why is because the rate at which they react does not depend upon the concentration of them.